Hi everyone, my name is Ryan Cardinal. I'm the technical lead on the FIFA gameplay team up at Electronic Arts in Vancouver. And I'm here with two of my colleagues, Luke Shier, who's a senior animator and is one of the driving forces on our team's initiative to motion capture a full soccer match with XSens suits. And David Wong, who's a senior software engineer working on animation applications of machine learning. And we're excited today to talk to you about FIFA 22's Hypermotion technology. The term Hypermotion was coined to represent the technology behind FIFA 22's gameplay features exclusive to the PlayStation 5, Xbox Series X and S, and Stadia platforms. From a development standpoint, Hypermotion represents our team's work that we did to combine real-world data and machine learning in order to make the animation in our game more authentic and seamless. It's our goal today to share why and how we pursued these goals and to share some of our results. We'll start by taking a deep dive look into the full match capture session we did using XSens suits. We'll explore the motivations behind capturing a full soccer match in this manner and take a behind-the-scenes look at the shoot. We'll then look at the impact that capturing data in this manner has on animator workflows. We'll show how we reconstructed 3D ball data from the video footage of the shoot, and then look at some applications of that data. And lastly, we'll present how FIFA uses machine learning to produce procedural animation using neural networks. So without further ado, I'm going to pass over to Luke Shier, who's going to take us on a deep dive of that full match capture session.
Thanks, Ryan. When it comes to inspiration, the ultimate vision for us on the gameplay team is to recreate what fans see every weekend on the pitch, or at least a version of it that we can squeeze into our 12-minute virtual game. So it's only natural for us to always be wondering, what if we can capture what we see on TV? This has been a dream of ours for decades, and over the last couple of years, we have started to make huge strides to make it a reality. Our first exercise, though, was to list the limitations of our current optical setup. And the first problem comes from just the physical dimensions of the space. Optical studios are small when you're looking at it in the context of capturing a full game with 22 players. The second is a limited local talent pool here in Vancouver, sometimes leaving us wanting more when it comes to variety, authenticity, and the ability to perform actions based on professional reference. Now we can take our setup on the road and go to the pros. The main problem, though, with capturing an optical is that the motion can become artificial. It loses so much of that context and detail of motion from a real match. It also lacks the competitive atmosphere, the aggression, the creativity, and the emotion of football. We're looking to capture in the highest fidelity and realism possible, and doing this will only enable us to build a better game. So it brought us back to our goal of capturing professional players competing in a real football match on a real pitch. So the first thing we did was prototype and start small. We were familiar with sensor-based capture methods like XSens, and after reaching out to them to get a showcase of the latest quality levels, we were pretty optimistic it might be possible. So we arranged for them to come to visit us in Vancouver to help capture 4 players in a scrimmage on our studio soccer pitch. Here you can see the raw data from one of the suited players that we captured. We were really excited about the quality of the data we were seeing, and so we started to feel confident in exploring the idea of capturing a full match with professional teams. This prototype allowed us to see the quality level of the data, to prove out our pipeline and get this data into the game, and most importantly, allowed us to identify the remaining problems that we need to overcome to successfully pull this off. So what were these big problems that we needed to solve? Well, the first one was player drift. Sensor-based capture methods tend to experience drift on a character's route over time, and we were trying to shoot in 10 to 15-minute segments, which lets the athletes get into the flow of the game. Once we got this data back, we measured over 12 feet of drift on the character's route by the end of the take, which was quite large. The other major problem is we didn't actually have a way of capturing the existing 3D ball data. It's a critical piece of data needed for understanding context around player motion. We needed a way to reconstruct this ball data. In order to resolve the player drift, we used a local positioning system, or LPS for short, which is similar to kind of GPS, but instead of satellites, all we needed to set up was beacons around the pitch. Players then wear a chest strap with a sensor, and the beacons can pinpoint the player's location to within 5 centimeters. We ended up using the WeMove Pro sensors, which is the same tracking system used by clubs like Barcelona and Real Madrid. And with the help of XSens, we were able to integrate this LPS positioning data into the animation solve to correct our drift issue. Next up, we need to somehow generate the 3D ball data. Ball data is really important information that provides a lot of context to the motion that we see. It's the focal point of a sports broadcast, so being able to follow it with the camera really helps follow the play when playing back our solved scene. So for the problem of generating the ball data, we use static camera footage to reconstruct 3D ball position, as Ryan will cover shortly. So two solutions to our two main problems. Our dev team started searching for teams that we could partner with for the shoot. Everything was coming together to be able to do this in spring of 2020, but unfortunately, COVID had other plans. As the world shut down, our dreams were put on hold and we had to defer our plans to some unknown future date. We weren't ready to give up just yet though. As sports leagues started up again, we continued to look for opportunities, and opportunity arose to work with two professional Spanish teams. Also, due to travel restrictions, no one on the FIFA development team was actually able to make the trip to Spain for this shoot. Several members of our animation and production team joined the shoot virtually. We partnered with a company called RenderMotion, who provide XSens-based animation solutions in Spain to perform this shoot for us. And with that all being said, let's take a look at what we needed to make this thing work smoothly. At the beginning of the video, you can see the players are standing in little hoops facing a piece of tape. These mark the positions and orientations in which the players needed to start this take. And having a well-defined relative position helped us when we were building a merge scene of all of these players. We also got the players to clap at the beginning of the take, as you can see as well. This action helped us synchronize the video footage with the XSens data. So in order to be able to reconstruct the ball positional data, we needed to capture the action from multiple static cameras. 8 cameras were set up around the stadium to capture everything, as you can see on the right. We captured 8K video at 50 frames per second, which is about 270 megs per second. So make sure you're stocked with SD cards. Also in the video, watermarking absolute time code, which is real world time. On the video, it allows us to synchronize the camera footage with the motion data, which we were capturing, which is a critical piece. So during the shoot, each take was at least 10 minutes. This allowed players to get into the rhythm of a game and help our goal of capturing better performance. The takes were ended naturally on the next whistle after the 10-minute mark. However, we had a hard cap at the 15-minute mark and the referee would blow the whistle to end the take there. Long takes are cumbersome to work with in our animation tools, and as the file sizes of the captured data and video footage become massive. So having these breaks keep things reasonable and provides an opportunity to swap SD cards, fix sensors on the suits, etc. And lastly, the long length of the takes, the flow, the intensity, and the performance were amazing. We were so happy with the data we were able to capture. So once we completed the shoot and after a bit of back and forth, the final data was delivered to us for us to start working. Here you can see the delivered data retargeted to our rig. It's hard to follow the play without the ball. Also, as an animator, it's tough to identify exactly what portions of animation we would like to extract, not to mention all the context around the movement of players and how it pertains to the ball itself. So now we'll just do a quick run through on how our team used the data from the shoot in different ways. One of the primary driving forces behind this shoot was to be able to do a large animation refresh with authentic motion to the sport. The kicker in capturing data this way is it requires a whole new workflow. When we run an optical shoot, animators create a shot list with all the animations that we need to capture. The talent then tries to perform all the shots on the list under direction, and then animators select the takes that they like. Each delivered take is a short piece of animation with a specific action. When we capture in a full match contest, we're sorting through 22 different players' data. Each file is 15 minutes long, and we have no way to find the motion we like out of the box. We needed a new workflow to be productive. Each individual player's data is merged into a single master scene for the take, which is then augmented with the ball data. A camera is then attached to the ball. This allows animators and designers to watch the game similar to a TV broadcast. And every time they see something interesting, we record the frame the motion started, the type of motion, whether it's a dribble, a tackle, a kick, etc., and a short description of how that animation can be used in the game. We're effectively building a shot list in real time as we watch the game back. We can then go through this shot list one by one or feature by feature and export the frame ranges we're interested in. Here's a great example of a highlight from the game, just a beautiful free kick that results in a goal. So once we've identified this, the animators will go back and identify the start frame at the bottom and which player performed the action, which you can see on the right. So once we've identified the player and the frame range we're interested in, we load up the single player file, scrub to the start frame, and export what we need. A naming convention is used on the exported file so that animators know the source file and frames of the exported data. Animators can then clean up and modify the exported portion as we see fit. And now I'll share a few examples from the shoot compared to the source video and then how they turned out in the game. First, we start out with this great goalkeeper save. The keeper reacts really well to this deflected shot and swats it away from goal. And this is one example of a scenario that's really difficult to recreate in our studio. Next, there's this beautiful slice lob with a great follow through. As it sails across the pitch, the player admires the pass. It's details like this that create stunning, unique animation that we're always looking out for. And lastly, here's another scenario that's difficult to capture in the studio. In Mocap, the actors use slide mats to recreate sliding tackles or kicks. They need to focus on hitting the mat, contacting the ball, instead of just sliding naturally and doing what they do. This particular animation came from two players fighting to keep the ball in play, but even played back on a single actor, the effort shows through and improves the situation. All in all, our animators were able to add over 4,000 new gameplay animations this year, and a huge chunk of that was from the XSens data set. Now I'll pass over to Ryan to talk about the ball generation.
Thanks, Luke. So the easiest way to follow sports is to follow the ball. And we needed that 3D ball data in our animated scenes so that our animators can follow the play in their tools. And as we'll cover shortly, we needed that to be able to extract portions of the animation that interact with the ball for use in training our deep neural networks. So let's look at how we augmented our animation data with 3D ball position data and see how just by having that data around, we can use it to find solutions to other problems. The only information we have available for recreating that 3D ball data is the static camera video footage from our capture session. The information that we need to acquire are the 2D screen coordinates of the ball from the various videos and the projection matrices of the cameras. These pieces of information will allow us to project a ray into the world from the camera through the tracked object, similar to how you would click on a 3D object using a 2D mouse cursor. We can then estimate the projection matrices using a computer vision technique known as camera calibration. And then by using multiple calibrated and synchronized cameras, we can shoot multiple rays into the world, and the closest point between those two rays will give us our object's location. So let's take a quick look at how we track the ball. Here you can see the tool I built. It was just a simple video player I built using Python and OpenCV that provides support for tracking. And since we're in control of the parameters of our capture session, we're able to cheat a little bit. So by choosing a ball whose color stands out from its surroundings, we can simplify our tracking logic by using HSV blob detection. And this works by converting the red, green, and blue pixel values into the HSV or hue, saturation, and value color space, which looks something like this. And we can then convert those pixels into a binary format where the pixels will be white if they're within the desired HSV range, or black if they're outside of that range, which looks like this. And then the center of our chosen contour will be the ball screen coordinate. There it is. To calibrate our cameras, we then need to provide the calibration algorithm with many sets of 3D object points and their associated 2D coordinates. The idea is that given many examples, the algorithm can estimate the projection matrix needed to perform such a projection. So traditionally, you would do this by filming a checkerboard pattern from many different angles. However, we didn't have access to the cameras, so we needed a different solution. So what we did is we associate the known landmarks on the field with 2D screen locations using a simple tool pictured here. And once we do this for all of our camera views, we can run the calibration algorithm to produce our projection matrices. And then once we have the calibrated cameras, we can write a script that triangulates the ball position and injects it into our animated scene. And here are the results of the ball being added to our motion builder scene. And while it wasn't perfect, it allowed us to work with and review the data much more easily. And it provided the context necessary to extract the motion needed to train our neural network for machine learning. And while this ball data was primarily used to help our animators and for machine learning, just having this data allowed us to use real-world ball trajectory data to improve our in-game ball physics. Historically, we would tune ball physics against reference videos. However, the solution isn't very scalable. It's slow and tedious, and while we might improve a scenario that we're testing, it's difficult to avoid regressing in another case. So we felt that if we could get a lot of example trajectories from our XSens shoot loaded into our gameplay testbed, we could build a system that allows us to iterate on our physics parameters and test against a wide variety of different ball trajectories quickly. So we developed a system that loaded a set of ball trajectories. It would then select one and launch an in-game ball with the same initial velocities. We could then compare how the ball travels in our game versus the real world. The system allows us to rapidly compare and validate our tuning against a whole battery of cases in order to ensure we're continually moving towards the right direction. And here you can see some examples of the new ball physics in action. And now I'm going to pass over to David Wong, who's going to show us how FIFA uses machine learning in our animation system.
Thank you, Ryan. Now we'll cover the machine learning part of Hypermotion, specifically the ML flow system. The major advantage of machine learning is that it can solve hard problems where traditional coding can be difficult, but it also requires lots of good data where the solution of the problem is embedded in the data itself. Previously, our team already has had success shipping small ML components like ML-based head tracking and ML-based IK, as you can see in this video. However, the scale were relatively small, with very small neural networks, a customized specialized ML inference runtime, and the only control a small number of joins. We want to scale up to solve larger problems. First, we will need a more generic ML runtime inference solution to support many more different operators. Because we want to test different neural network architecture, we want to experiment with different ones. So our ForceBite team have developed this by wrapping over existing open sources like Cafe2 and Onyx Runtime and port them all to all target platforms, optimize and trim out unneeded code. This is what ML4 is trying to solve. In FIFA, two of the primary actions are moving player from one position to another called locomotion. And to make ball contacts, such as kicking, trapping, passing, or shooting, we want the transition from locomotion to ball contact to be smooth and seamless. An example is shown in this video. GDA is the development name of ML flow. When no GDA or ML flow is on, the player did a hop during the transition due to phase mismatch. With GDA, transition is smooth. ML flow tries to solve this transition problem. These are the main inputs to the neural networks. We have the starting and current pose with the full skeleton. And then we have a target pose in the future with simplified skeleton. And we have the locomotion path from the current pose to the target pose. And then we have target time and other control parameters. The neural network model outputs the next pose 2 ticks into the future with foot plan state and some others. If we repeat these steps, we will generate all the poses in between, and it forms a transition animation, as you can see here. This is a step-by-step generation showing the output of the neural network per frame. We have a system called pan path that calculates ball contact animation and path to that animation. Output from pan path used as inputs into ML flow. Pan path can change decision every frame, which means ML flow needs to respond to requests to preserve responsiveness. As a result, depending on the data coverage, we can't guarantee a seamless transition every time, but in most cases, it produces good results. In other cases, we are not worse off than what we were previously. We would love to have everything 100% seamless. However, our top priority is to be responsive to our user input. To get the best authentic motion, we want the data to exhibit the characteristic of real football players, which is why we felt using the XSens data was vitally important for us. It gives a fairly large data set, and the player weren't acting as would be in Mocap section and have a lot more space on the field than in Mocap Studio, which Lud already mentioned before. This is a diagram of a high-level overview of our data pipeline. We export the animation to more ML-friendly format from various sources. Even though we obtain a lot of data from our XSens suite, but it's really only one match. It's limited by the action performed by the athletes in that particular match. The coverage was not enough for all the possible cases in our game. As is common in ML, we need to do data augmentation. We use optical mocap data that we already have, and we also use our game to generate more artificial data where we measure the quality before adding to our training set. And we did another section of mocap to fill data holes. To train the DNN, the deep neural network, we extract the input features and output labels from the CSV data. We use PyTorch to train it on the cloud AWS. We use TensorBoard to monitor the training progress. We have about 5 million data points to train per network. Once the network has finished training, we put it in our game with our runtime inference engine, as we mentioned it before. Then we can go testing in our game. One common question people ask is, how long does it take to train? It first took a few days, which was totally not acceptable nor practical in production. So we aggressively optimized it down to 2 to 3 hours via neural architecture, distributed training, tuning the learning rates and other parameters. Besides training time can be slow, one commonly overlooked area is the data processing time. It could take a very long time, so we optimize that too, using multi-cores and multi-machines. We were able to leverage our gameplay testbed to create a stress test scenario for our system. We set up random scenarios where the ball and player would be launched from different starting states and have the player intercept the ball in different ways. These tools provide a way to do A/B testing. It will run the same scenario once with the ML flow system enabled and once with it disabled. We can also leverage this system to compare iterations of our networks by supporting hot swapping of our ML models between runs. We derive quality metrics to measure quality like foot sliding, momentum pops, post error, etc. We run thousands of this scenario overnight and get a report of their metrics to compare. Tens of thousands of these scenarios would run overnight and a report will be available in the morning. We will see statistical analysis of the number and types of error we were encountering. We use Python to analyze and extract specific information that we wanted. We visualize the path coverage with heat maps, path patterns, and generate histograms. The report also tracked the scenario inputs. We needed to recreate the individual tests so that we could retest the scenario against a modified neural network model or other fixes. We can identify data holes by visualizing the heat map, as is shown on the picture, of the trajectory coverage and checking all the worst cases. We also use the stress test to identify scenario where ML flow was behaving poorly and the old system was behaving nicely. We could then go back and export the data from the scenarios using the old system in order to augment our training data. The quality metrics are very important to measure incremental changes of the network model features or data, since each change might make some improvements that is very hard to tell by purely looking at it. The ability to iterate and stress test changes and measure quality and performance was invaluable. The bottom line is, if you want to build fully procedural ML animation system, you likely want to build an automated ways to validate the quality of your system. Here we can see some example of ML flow in action. The players will adjust the cadence by taking stutter steps or elongating their strides in order to take the ball in stride, as you can see here. There's some more examples. I'll pass back to Ryan. Thank you.
Thanks, David. So I guess it's about time we wrap up our talk. But before we go, I just want to summarize our team's experience trying to deliver on Hypermotion, what worked and what needs improvement. In terms of what worked, we accomplished our initial mission of capturing a full soccer match between professional teams. The animation delivered was high quality, and we were able to capture a lot of unique animations and scenarios that were previously not possible or at least very difficult to capture in a studio setting. We successfully generated ball data, which provided additional context for the motion, allowing animators to follow the play and providing examples to help improve our physics. And it provided lots of animation data with unique and desirable characteristics that we used to train our neural networks. And while we're very happy with what we accomplished, we need to acknowledge that there are considerations to make if we want to continue to efficiently work with lots of big animation data going forward. we now have a new problem of identifying, selecting, and exporting animation data that we want to use. And we now deal with large file sizes, which take longer to load in our tools. So we need to invest in finding an efficient way to categorize or tag animation with relevant context so that we can build a tool to search for the specific motion we're interested in. In conclusion, we feel very positive about the steps we took this year. We've added a new capture technique to our toolbox to help augment the visual authenticity of our game, and we're able to leverage this data into adding the largest number of gameplay animations into our game in a single year, and to improve the game's ball physics. We also built our first machine-learned animation system that generates full body animation, and our team got more experience productizing machine learning features, which gives us more confidence to take on more ambitious or difficult problems in the future. And that's what Hypermotion represents to our team, blending real-world data and machine learning to improve the authenticity of our game in meaningful ways. And that's all we have for you today, and thank you very, very much for listening. And before we go, if you're interested in machine learning in the animation space, our colleague Sebastian Stark is going to be presenting tomorrow morning at 9:30 a.m., where he's going to cover 4 years of research in the space. Sebastian's an AI scientist. He's really smart, funny, and he's an engaging guy, and his talks are always fun, inspiring, and informational. So I highly recommend you check out that session. And lastly, we're always hiring. So if you found the work we presented interesting, we'd love to hear from you. There's a few minutes for questions if you want to step up to the mics. Yeah, we should have a few minutes. And if we don't have much time, then our contact information is on the screen, or you can contact us through the conference app.
Hi, I was wondering if you could elaborate a little bit more on what parameters you were using for the machine learning to know that it was effective, like a perturbation was effective versus a previous perturbation.
Right, so we have a system that we didn't talk about today. It's a quality evaluation. So essentially it will score the quality of the animation. It takes short samples of animation, and it's another machine learning system that will score that quality. It's a generative system, so it generates a pose based on the previous animation, and we compare that to the pose the animation in-game generated. And based on the score, we can evaluate the difference between those poses. The other systems we use are more heuristic-based, but looks at foot sliding, scissoring, and stuff like that.
Cool, thank you.
Hi, nice talk, thank you. I was wondering, during the full motion capture on the soccer field with two teams, you mentioned that you are creating your shot list, watching the result of the mocap, if I understood correctly. And I was wondering, with the full liberty given to the players, it seems that inherently there would be a lot of ambiguity in the data with respect to the features that you use to drive the characters. And so I was wondering, did you pay any attention to how to remove that ambiguity, or does your system is able to handle it?
Luke, did you want to take that, or take the capture side of it?
Yeah, with the shoot, we had 2 full teams. And sorry, one question. What do you mean by the ambiguity with the data?
Simple example: if you ask your character, if you think your character is running forward, there are many different speeds, many different things that happen. If we just consider that parameter of forward speed, so I'm thinking that based on your set of features, your set of parameters for the motion, there would be a lot of different motion that would fit the same values for those parameters. Does that make sense?
Yeah, that makes sense. Yeah. So we treated this shoot as kind of a cherry on top, and to help drive future technologies. So a lot of our fundamental gameplay animation systems had a lot of the animation in place that could, make the feature run, and we were able then to be very selective about what animations we wanted to pull out to put into our game. But in the future, it will be much more dynamic and complex, because we do want to pull out a lot of these different pieces, whether they're sidestepping at certain speeds or how they move to the ball. Being able to categorize those and extract large portions so we can pull them out is really important, but we haven't got there just yet.
On the other side of things, it's not our only source of data. We have lots of optical capture that we still do. Like, it's not our only motion capture source. In terms of the neural network, how we choose the right portion of animation, there are other inputs to the network that are taken into account. So for instance, the locomotion path, the path that takes us from the current position to the target position, that has a time associated with it. So we know roughly how fast we need to get to that target pose. So that will help bias what we're selecting from the data set.
All right, thank you.
Thank you very much.
Thank you.
Thank you.